So at this point of the course, after studying the generic quantum formalism, we could take two routes. One would be to study the most famous example of physical degrees of freedom, which is the material point, an object characterized by position and momentum. But this requires more advanced mathematics, and we were going to do it in chapter 4. So in the chapter 3, we rather study the simplest mathematical vector space that gives non-trivial results in quantum mechanics, which is C2, vectors of two complex numbers. And the systems described by this vector space are called two-level systems or qubits. Now, what kind of physical systems do we have here? Many examples, but the most famous ones are written here. We have already seen in the first chapter, in 6 quantum pieces, the polarization of a photon that can be horizontal or vertical, can be plus 45, minus 45, can be circular left, circular right. There are always these two states that can be distinguished. Another very famous example that you've already encountered many times is the spin 1/2, which is the intrinsic magnetic moment of many particles, of all the fermions, electrons, protons, neutrons. This is also a two-level system. It doesn't have a very intuitive classical meaning, but it's a magnetic moment. It's something that is a kind of a vector that feels magnetic fields. You can also do two-level system theory for systems that have more levels. For instance, you can have the levels of an electron in an atom. There are many levels, but for some reason, you address only 2 of them. And the others you don't see, because you are able to prepare systems here, to do transitions with this frequency, and so on. So also here, we would have a system, the theory of two-level systems, and non-trivial effects, like for instance, the physics of atomic clocks, is done exactly in this setting. And another example, finally, just to continue with examples, would be an interferometer with 2 paths. I've drawn here the Mach-Zehnder interferometer, the Michelson interferometer. In both cases, there are only 1 and 2 paths, or 1 or 2 paths. And again, here, the theory of these objects, of these interferometers, would be done in with the same mathematical formalism. So let's now move to the mathematical formalism. What do we have? Again, I said before, we have the C² vector space, which means we need vectors of 2 components, each component being a complex number. The obvious basis, what is called the computational basis, is 1, 0, 0, 1. Depending the context, these vectors have different names. Now, this is a matter of flexibility. You will learn it. It doesn't really matter. In the qubit notation, quantum bit, we call the 0 and 1. In the spin notation, it's called up and down. In a more abstract notation I will explain later, it's called plus z and minus z. There can be h and v, whatever. These are these 2 vectors. And these are the eigenvectors of a matrix called sigma z. The first one for the eigenvalue plus 1, second one for the eigenvalue minus 1. And we are going to see more of these matrices. Another frequently used basis is the basis of the diagonal state, written again plus or minus, left or right, plus x minus x, depending on the notation. These are these 2 vectors. You can check that they are orthogonal. You can also check that they are the eigenstates, the eigenvectors of this matrix called sigma x, again for the eigenvalues plus 1 and minus 1. We've already mentioned something about the vectors. Now let me say something we are going to study in this chapter about the linear operators that obviously are 2x2 complex matrices. It's traditional to introduce a basis of such matrices that are called the Pauli matrices. They are written here, sigma x, sigma y, and sigma z, also known as sigma 1, sigma 2, and sigma 3. Together with the identity, they form a basis of the space of matrices. This means that any 2x2 complex matrix can be written like this, as a linear combination of complex coefficients and these matrices. And this object here is traditionally denoted as a vector formal scalar product with a vector of matrices. This is just a notation, and don't be scared by that. In particular, if the matrix is Hermitian, then all these coefficients are real. Now, let me do a connection between these and the vectors that is very important for this chapter, which is the connection of a generic state with the Pauli matrix, of which it is an eigenstate for the eigenvalue plus 1. A generic state can always be written in this way, up to a global phase. Real number, the phase, and the complex number that is the square root of 1 minus that thing square. Now, this state is an eigenstate of a matrix that is n times sigma, like here, with this vector n given by these coordinates. This is called the block vector. Now, if you look at what this is nothing else than a direction on a sphere parameterized in spherical coordinates of on length 1. There will be a r here that is r equal to 1. So what is the meaning of the block vector? At this mathematical level, the block vector is a label of the state. That's why we have written here in the cat. To explain what is a label, I just want to make an analogy so that you don't get too scared. Now, when you buy a T-shirt, essentially you go online, and what you see a label. You see the label, the color, and the size. These are two numbers or two letters or two pieces of information. You order a T-shirt based on those labels, and what you get is a real T-shirt. So similarly here, if I were to ask someone to create a state of a qubit, because I want the qubit to be in that particular state, in this state, what I would give to this person is the block vector. That's the label. What I want to get back is not a vector like this. I want to get back a quantum state, a two-level system in that state. In some cases, like in the case of spin 1/2, the block vector has a physical interpretation. It is the average value of the magnetic moment. In other cases, like the two energy levels in an atom, the block vector is more an abstract representation of the state of the quantum system. Also in this chapter dedicated to two-level systems, we shall have a look at the dynamics of a two-level system. Remember that the dynamics, we said in general, is described by the Schrödinger equation. The time derivative of the state is essentially the application of the Hamiltonian, again, an operator, in this case a 2x2 matrix, on the state. The Hamiltonian, remember, is a Hermitian operator. Therefore, for qubits, every Hamiltonian has this form, with E0 and E real and M of length 1. Now, of course, depending on the physical situation, where it's polarization, spin, interferometer, anything, these numbers and these will have different meanings. Now, the eigenvalues and the eigenvectors of this Hamiltonian are very easily found. The eigenvalues are E0 plus E and E0 minus E. The eigenvalues of every Pauli matrix are with plus and minus 1. The eigenvector plus M minus M. We shall see a case study, which is very important. Maybe we'll not do it in detail. It is the case of a two-level system with energy difference h bar omega 0 that is probed by an oscillating field. The field is oscillating at frequency omega, so period 2 pi over omega, and it has an amplitude h bar omega 1. The Hamiltonian looks like this. You can check that it is of this type with this vector varying in time, cos omega t x, sin omega t y. This phenomenon describes very important, the Hamiltonian describes very important phenomena, the Rabi oscillation and the Ramsey interferometry, that in particular this one is used in atomic clocks and in nuclear magnetic resonance or magnetic resonance imaging. So we are going to discuss in a sort of qualitative way these applications of quantum mechanics.